welcome. This is the ideal gas law. And it's going to tell you how gases will act in an ideal situation, in a perfect scenario. And we know that it won't always be perfect, but we're just going to pretend it is. Anyhow, I know that you already watched a video on this, but I want to just kind of have this so you can see it, and I want to do my own video. But let's look at what everything is. P is pressure. And I think you have a vague idea what pressure is, but you don't actually know the official definition, so I'm going to tell you that right now. Pressure is actually the force per area. And the best explanation I have of pressure is imagine if you're walking in the snow or on mud or anything that you could sink into. Would you walk on snow wearing high-heeled shoes? Let's see if I can draw a pair of high-heeled shoes. Would you walk on snow wearing high-heeled shoes? And the answer is no, because you would sink. Okay, but maybe or maybe not, if you've ever seen a pair of snowshoes. Have you seen a pair of snowshoes? They look kind of like they look kind of like tennis rackets. They're like this, and then they have almost like wicker furniture, and then your shoes strap in right here. I know that's a very terrible drawing, but that's okay. And you won't sink if you wear these in the snow. The reason is your weight is the force. The weight of your body is the force pushing down on the snow. But the difference here is the area. Here, the area is very small. All that force is being concentrated right here on that heel of those shoes. So the area is small. So when you have the force divided by a small area, the pressure is very high. That's why you sink right into the snow if you're wearing these. Now let's look over here. The area of this snowshoe, it's like I said, it's like a tennis racket. It's very large. The area is much bigger. So because of that, the force of your weight is being distributed, is being spread out over the whole thing. So instead of all the pressure, all the force being concentrated right there on that point, the force here is being spread out over the whole thing. So the area is bigger. When you divide force and area, you get a smaller number. So that's why the pressure is much lower here and you don't sink. So that's pressure. Like I said, I think you knew what pressure was before. This is the technical scientific term of pressure. What else do we have here? Volume. You already know that. I don't think I need to go into that one. Let's see. N is the number of molecules or particles or atoms. Whatever. Any of those. Molecules, particles, atoms. All right, let me zoom out just a little bit here. Molecules, particles, atoms. T is the temperature in Kelvin. We use the Kelvin scale because it starts at 0. Everything is proportional. Hopefully you watched that video and you understand. And there's no negatives because a negative number in this equation would kind of mess everything up. And then last but not least is R. What is R? R is what we call the gas constant. And it's a number that doesn't change, so you don't have to worry about memorizing R. It is what it is. Anyhow, it's just the gas constant, and that number will be given to you, so don't get too worried about it. But that number for the gas constant is 8.31441 joules per Kelvin moles. I don't know. Okay. So those are the units, but like I said, that will be given to you, so there's no issues there. But what I do want us to understand is what's actually going on in this formula and how things change. And so I have some, hopefully, visual aids that'll be helpful for us today. So let's go back to PV equals nRT. To R value, this is a constant, so it will never change. And right now I'm going to show you a quick trick to knowing if something increases and something decreases. Now the trick will work, but you have to remember the trick. So if you're comparing two values on the same side, then one will increase, one goes up, and one goes down. For instance, if you're comparing pressure to volume, if pressure increases, volume decreases. If volume increases, pressure decreases because they're on the same side. Well, if that's what's going on, then two values on different sides, they will do the same thing. Both go up or both go down, one or the other. So if you're comparing pressure to temperature, if the pressure increases, the temperature will increase. If the pressure decreases, the temperature will decrease. So if they're on the same side, they'll do different things, and if they're on opposite sides, they'll do the same thing. That is a very quick description of this equation, but that also does not help you understand anything. So now I'm going to try and help you understand things. And we're going to have balloons here. Now we're only ever going to compare two quantities at the same time. Oh, that's not a good balloon. That's okay. We're going to have two balloons here. The same size. Those aren't the same size. Let me try that one more time for you. Two balloons of the same size. That's better. Two balloons of the same size. Okay. And I'm going to draw bigger balloons. Let's try this one more time. I promise I'm going to get really good at drawing before the end of this. Oh, I just had a great idea. Now we know they'll actually be the same size. Okay, here we go. Two balloons. We'll make them balloons. Two balloons of the same size. So here's what we're going to do first. We're going to put some molecules in here, and for that I have peanuts, because what else do I have? Let's put 8 molecules in here. Okay? So our N equals 8. Okay? And over here, I'm going to put 4 molecules. Okay, and here's what I want us to imagine. So if I change the molecules from 8 to 4, and you have to imagine these molecules, think of them as people that are in this confined area. They're all moving around, they're all bumping into each other, right? So they're bumping into each other, and they're creating pressure. And then here there's only 4 people, and they're bumping into each other and creating pressure. Where is there more pressure? Like if you were in a confined area with 8 people, or you were in that same area with only 4 people, would you feel more pressure where? And I think all of you could tell me there'd be more pressure here because you'd be bumping into more people. There's more force, there's more pressure here. There's less pressure here. And how much less pressure here? And I'm going to make up a number, but let's say the pressure here was, let's say the pressure was 10. Because the number of people or the number of particles got cut in half. So if we think So like I said, the number of particles got smaller, and so the pressure actually got smaller. Well, it would actually get cut in half as well. So if that cut in half, then this would cut in half. So if the number of particles cuts in half, the pressure does cut in half as well. Okay? Hopefully that made sense. All right. Great particles. Okay, this one now, let's try that one more time. I'm going to draw you another balloon. And then I'm going to draw you a smaller balloon. Okay. So, how about this one? So here, let's say the volume is 6. And here, let's say the volume is 3. In each of these, we're going to put let's put 5. Oh, let's put 8 in. Okay. So 8 molecules here. And let's put 8 molecules over here. Hold on. Let me get one more molecule for you. 8 molecules. Okay. So which one is there more pressure? In which balloon are they feeling more pressure? Over here, they're more spread out. They can move easily. There's 8 of them. And they're not bumping into each other. Over here, the volume's smaller. So they're bumping into each other more. And there's more friction. You know, maybe they're angry because they're bumping into each other. I don't know. But the point is, as far as pressure goes here, there is going to be more pressure here because they're bumping into each other more, and less pressure here. And once again, let's say that our pressure was, let's make up a number again, 10. Here, because the volume got cut in half, it went from 6 to 3, that's half. Here, the pressure, we can agree that it's going to increase because the volume got smaller, so there's more bumping. The pressure is going to go up. Pressure will go up. And how much is it going to go up? If this got cut in half, this got divided by 2, then this is going to get multiplied by 2. So here the pressure would be 20. Okay? So you can kind of look at these things, you can compare them, and we can figure it out. But yeah, they're going to always relate. So you want to try and think of, if there were balloons and these particles are floating around, what's actually going to happen. All right, so finish up this video. Well, it's over now. And I have a few questions for you to answer. So go ahead on to the next part and answer the questions. Thank you.